Welcome to our live webcast co-hosted by ISA, and thank you for joining us. My name is Mike. I'll be the operator for our presentation today. Now, before we get started, I would like to take a moment to acquaint you with a few features of this web event technology. At any time, you may adjust your audio using any computer volume settings that you may have. Located on the right-hand side of your screen, you see the Q&A window. There's a large window which holds all of your sent messages and a smaller text box at the bottom where you can type in your questions. Send a question, click in the text box and type your text. When you're finished, click the send button. All questions that you submit are only seen by today's presenters, and your questions will be responded to in the order in which they are received, will be addressed at the end of our presentation today. At the conclusion of our program, we ask you to complete a brief survey. If you would take a moment to complete this survey, as it will help ISA plan future web events. We are joined today by our three speakers, Rich Cole, Ned Espy, and Roy Tomolino. Rich Cole has been engaged in calibration and measurement uncertainty at various levels for more than 25 years. Beginning in the U.S. Air Force, he moved through several technical positions at automation companies until he joined Honeywell, where he has been for the last 27 years. His experience includes implementing 17025 in a field service organization, managing a proficiency testing program, providing 17025 technical training, and maintaining laboratory and field uncertainty budgets. Ned Espy, Technical Director, has been promoting calibration management with Beamex for over 20 years. Ned has helped develop best practices for calibration with a focus on pressure, temperature, and multivariable instruments. He is a consistent editorial contributor, to leading industry publications and has received significant recognition within the automation industry. Today, Ned teaches calibration best practices and provides technical support to end users and the Beamex sales team in North America. Roy Tomolino has been teaching calibration management for almost 20 years. Throughout his career, he has taught on 4 different continents to people from over 40 countries. His previous roles include technical marketing engineer and worldwide trainer for Hewlett-Packard and application engineer with Honeywell. Today, Roy is responsible for all Beamex training activities in North America. So with that, I'd like to welcome our speakers to the program. I'll turn the microphone over to Ned to begin by going through today's agenda.
All right. Thank you, Mike. That was a good introduction, and I want to start us off today. We welcome everybody, and thank you for coming and joining us here. So what are we going to talk about today? Let's see. So we've already done that, but we want to talk about how do you bring laboratory practices into the field. And then Rich is going to take a deeper dive on problems you may encounter that can affect accuracy of your measurements. Then Roy's going to give us a demonstration on these issues. So after Roy does his demo, we're going to have a commercial break and go through a little video. And then we're going to get back talking. I want to talk about the topic of uncertainty and how you might apply it. And Rich is going to go into the details of what contributes to uncertainty, and then another demo by Roy. And then finally, we're going to end the session opening it up to Q&A. So please submit your questions through the chat room, and we look forward to that. Okay, so before we get started, we do want to ask you guys a question. And if you look, it says, do you include uncertainty data and analysis in your business? So we just want to get a feel for how many people are really focusing on uncertainty. Some of you may be in an industry where it's not such a critical need. So we're seeing the numbers come in, and this is good to know. It looks like about 2/3 of you do deal with uncertainty. And we'll keep that in mind as we go through these slides. So that's very good. So those that don't deal with uncertainty, it is something that you should be aware of, and hopefully will enlighten you a little bit today. So one thing I want to do here at the start is just make some basic definitions. Just get us all on the same page. So when we talk about calibration, just as a definition, it's an activity where an instrument, in our world we're talking about instrumentation, is being tested and compared to a known reference value. So the reference value is the key term. You need to be using something that is more accurate than the instrument that you're testing, and there should be some kind of pedigree, like an NIST certificate or similar, showing that it has been tested to a higher level accuracy. Also, when you make this comparison, the calibration typically involves documentation. People either write the numbers down or record the data some way. And, and the bottom line is after you perform a calibration, if there has been drift and you've made proper adjustments, you're essentially making the instrument factory new as when it was first shipped to you. So on the flip side, when you look at a process plant, the control engineer who's designing the plant to produce high quality product and in a safe environment, they want good data. If you're a technician and your calibration of an instrument for whatever reason is off, basically you're providing poor data or really bad data to the control engineer, and they cannot make good decisions with poor data. They need the best data that you can deliver. So here's some terms that Rich is going to go through a little bit later. He's going to talk about all these things because they contribute to a total error that you're trying to analyze. For me, for what I want to cover right now, I just want to focus here at the top and the bottom. I want to talk a little bit about accuracy and then introduce you to uncertainty. So this is a busy slide, but here's another definition. Accuracy represents the closeness of a measured value to a known reference value, or maybe another way is to say a true value. And, many times when we look at the vendors that supply both instrumentation and calibration equipment, they can be vague or, there's just a lot of things that you got to take into account into the accuracy statement. And some of these things that we mentioned on the previous slide may not even be included in the accuracy.
So, Ned, I'd like to make a comment here. With regard to your second bullet, this is kind of what we used to call specmanship back when I was in the lab. And what it comes down to is when you're looking at spec sheets, you have to be very careful and read your fine print on the spec sheet. It will somewhere tell you whether hysteresis and repeatability is included or it's not included in a particular spec. So when you see those asterisks or footnotes, go to the bottom of the page and check out what the accuracy spec that they're talking about really includes. So I just wanted to point that out. That we need to be very careful about reading our spec sheets.
Yeah, great point, Rich. And so when you're trying, as Rich says, to do some analysis, an apples to apples comparison, and here's an example. What if you see something that's a percent of full scale, but then on another device, it's a percent of reading, and maybe there's some fixed component involved in that. So these are typical or common ways to state accuracy. So here's the graph. So if you look at the full scale statement, it's this gold line up here, and this is 0.025%. If you have a statement that says it's 0.01% of reading and then a percent of full scale, like a compound statement, here's that base error, that 0.005% of full scale, and then here's the percent of reading piece going uphill on this slope. So in this example, this is significantly more accurate than this statement, but when you're doing this type of analysis, the only way you can compare different statements and specifications and all the fine print is to try to calculate exact error at particular points for what you're interested in measuring. And then finally, well, not finally, this is my second to last slide. I want to talk about how there's a hierarchy. At the top, the chart is showing a true value, and it expands down here to the process. So our audience today, you guys are at the process plant level making measurements with instrumentation, and if you're trying to calibrate, you want to show how you get back to the true value with some level of certainty. And when we talk about uncertainty, to make an estimate, it's a mathematical estimate or a statistical estimate with a given coverage factor or confidence level, which helps you get to the true value. And it can start getting a little tricky because we're pulling in statistics. And I do want to make mention that when you're looking at uncertainty, it's more than just numbers. Uncertainty involves humans. Humans can make mistakes. You're not, and especially our audience today, you guys are working out in the field. It's a cold day. It's in the middle of summer, a very hot day, so the environment can play a big factor. So there's other things that contribute to uncertainty aside from just the numbers that we're kind of focusing on today. But I guess good news is when a calibrator vendor analyzes the uncertainty of their instrument, they perform type A and type B type uncertainty analysis. And I'm not going to get into that detail here, but I guess the good news for the process folks is that when you get to the level out on the plant floor, your components almost always fall into the type B category. So you only have to have one method in analyzing things. And as a final thought, think of type A factors as things that are random, that you really have very little control, such as the environmental temperature when you're having to work outdoors. And a type B is more of a systematic type of error. It's something that you can maybe control if you can, work in a room that has an error, then that would certainly help you improve and make better measurements. And then the last term I want to throw at you is we do want to talk about expanded uncertainty. And expanded uncertainty is where you're trying to pull in all the different components and you're using statistics and you want to have a confidence level. This word confidence and, apply mathematics to it. So you've maybe heard of Six Sigma in quality programs. Well, Six Sigma provides a confidence level of near perfection. And in our world, I think we have a thing that comes up here. 2 Sigma is pretty much the norm. As an engineer, if you take an engineering standpoint, if you're in the ballpark, things are good. And if you have a 95% confidence level, you're kind of in the ballpark. All right, so that's an introduction to our presentation today. I'm going to let Rich take a deeper dive here, so I'm going to turn it over to Rich.
Okay, thanks, Ned. Before we get into the question, let's do the question first. Do you use 17025 accredited labs for your test equipment calibrations? And boy, it's coming in a little heavier toward the yes than our previous question. Like almost 80%. And that's coming back down. Okay. So I just want to make a quick note about, before we go on, about expanded uncertainty that Ned was just talking about. And this is something that's very important. You'll see this listed on your spec sheets and your calibration certificates as K equals 2. And it's important to take note of this because items that are going to be combined, contributing factors that are going to be combined to get your total error or total uncertainty, all have to be expanded to the same K-factor in order for you to perform the math to bring them together. So that's just something to watch out for later. So let's talk a little bit about calibrations in the field and the history of this. So what we're going to talk about here is how accurate is my calibrator, and how accurate is my measurement. So there is a difference between the two. Sometimes it's a big difference. And so the big takeaway from this section should be the accuracy spec of the M&T is only a part of the larger overall measurement accuracy. With that, we'll go on to the next slide. So in the good old days, when accuracy of test equipment was questioned, you might have gotten by pointing to a yellow sticker on it and saying it was just calibrated, so it's perfect. So you'll probably have to have been around a long time to remember these times, but once upon a time, calibrated and perfect were kind of thought of as the same thing. But that's not necessarily true, and let's see what makes the difference here. So then, a little bit later on in the history of calibrations in factories, you may have been asked about the specifications for your test equipment. Your calibrator accuracy spec of, say, 0.03 degrees C for your thermocouples. So now you've gone from a perfect calibration to a 0.3 degree error. This is kind of what we're saying is how accurate your calibrator is, going back to the initial question. But that's not all there is to be considered. Let's see what else we have here. So now you're asked about the process instrument, the process instrument, or the UUT, this is the unit under test. Has a published spec of 0.2% of span, plus or minus 1 digit. If we take that as a worst case scenario, we're up to 3.9 degrees C. Now your perfect test has gone up to a combined error of 4.2 degrees C. So that stated error is close under ideal conditions. However, in the drive for better accuracy, the figure is still not good enough. What we're seeing here is this is from the point of view of the process measurement. That's the end result of your calibration in the process instrument going. And you see we have a big jump in accuracy represented by the red line. So why isn't that good enough? It's because saying that the UUT is measuring, again, that's the process instrument, is measuring within 4.2 degrees could be misleading. Any of the test equipment specifications that are published are usually backed up by details showing how the number is derived and what can affect them. So let's call it the fine print. This is what I was talking about earlier with does it include various contributing factors or does it not? So I think we can move forward and we can look at an example of one of these and how it affects the overall uncertainty. So now let's say that one of these fine print items could affect your example. So we look at the big hitter we left out is the 0.2% accuracy adder for using internal reference junction compensation. So most everybody in the field is going to be using the calibrator's internal reference junction compensation. So it's almost a default add for the field. If you didn't use that, you would have created an external reference junction compensation, which has its own sources of uncertainty, which you would have to add beside that. So now we're looking at this increase of spec just from the point of view of the measuring and test equipment. So again, in this case, you started out at 0.3, you've gone up with a 2-point adder to 0.5. You've almost doubled your specification of your calibrator, and this is just looking at one of the components that you have for contributing factors to your calibrator's accuracy. So that's just the beginning. There's a bunch of other a bunch of other contributing factors that need to be considered when you're looking at total uncertainty. So we have temperature coefficients, common mode error, temperature gradients along extension wire, if you're using extension wire. Even the calibration of the test equipment itself has an effect on the how accurate your measurement is. So once you add up all this stuff, your actual UUT might be measuring much worse than 4.2 degrees C. And so how much worse, we really don't know at this point. You have to calculate it all out, and before you can do that, you have to understand your calibration and understand your test equipment to find out what's really going on with your measurement. Oops. So with that, I think Roy has a demo that he wants to get into, and so take it away, Roy.
Hey, thanks, Rich. So this is Roy. What am I doing with my jacket on? So let me end up sharing my screen here. I'm in Colorado. It's snowing outside, so it's a bit cold. And yeah, I'm in Colorado, so it might get a little smoky in here. Just send me a quick note to go like this if you're having trouble seeing me, because that'll clear the smoke right out. What I want to do is, I am a good example of a bad example. First, I need to load up a couple tests. I'm going to do a calibration. So let me send over these two tests. So at this stage, let me disconnect this guy, and now I'll load up my calibrator. Da-da-da, sending them over. Okay, so now it's sent over. Let me minimize this, fire up my calibrator. So we'll be doing a live calibration, actually two of them. This first one is our bad example. I have a PT207 with the wrong standard that I'm going to use. And where we're headed here is there's way too much uncertainty in the standard that I'm using on this one. So PT207, wrong standard. Here's what I got. I have a transmitter that we're calibrating. This one happens to be a differential pressure. I am hooked up to the high side. My low side is open to atmosphere. I'm running my MC6 calibrator, and you're seeing a live reading on the screen. This is not an emulator. You're seeing exactly what's going on right in front of me. And then I have a pressure pump that I'm using as well. So I have a three-legged hose. One is going to my unit under test, the second one to the calibrator, and the third to my pressure source. And this is showing me where to plug in. I need to be on this pressure module, which, you know what, this did pick the correct pressure module, but I want to pick the wrong one to prove a point. And I need to hook up here across the bottom, so I'm powering up the transmitter at the same junction where I'm measuring current. And that's across these two right here where it says loop. So again, I'm measuring current and providing loop power. And this happens to be a square root transmitter. Let me hit the check mark. First off, on a differential pressure or a square root transmitter, we never want to calibrate it at 0. First, let me zero out my transducer. And before I hit start, I'm going to use my fine-tune knob and get me up to about 1%. So this is a 207-inch of water transmitter. And I'll get us around 1%. 1% would be 2.07, and I can go a little bit higher. Notice that at 1% input, we have 10% output. So that's the definition of a square root transmitter. And I have a 4-second delay in between each one. The bottom right is telling us where we're going next. The center line is 0 error. The blue lines represent our tolerance. I've got the tolerance set up as a quarter percent of span. This happens to be a critical transmitter in the process. So normally we'd be looking at about 0.5% of span, or maybe 1% if it's not critical. So this looks like it's absolutely right on the money. My final test point. And notice I don't have to get it exactly right on. It's looking for 207. It can calculate what the output is against that input, and that's giving us our error. Let me go down. So I'm done with this test. And Clark. All right. I was thinking Clark Griswold, but we'll go with Clark Kent. And again, that looks really good. Here's our numbers. That looks really good too. And let me put in my environmental info. So it's probably 70, we'll say 72 degrees. My humidity, I am in Colorado, so that's really low. We'll say 15%. And let me save it. I'll save it as both as found and as left. Here's what I have. I can unload this into my calibration software. I just did that. And let me show you what that looks like. This is my calibration certificate, and I want you to see the graph. The blue lines, again, represent my tolerance, and any calibration software worth its salt should automatically calculate your uncertainty of the test standard that you're using. And the software that I'm using here is calculating exactly that. It's calculating the uncertainty and the expanded uncertainty. So if we look at our first test point, our second, let's go to our third one. You can see what we call guard bands above and below the test point. And that means that with that uncertainty, our test point could literally be anywhere along there. So this could actually be a failing test point if it's all the way up here. And this is the whole point with calibration uncertainty. I'm going to come back and do another demo that'll show you a good example. One final thing is, if I scroll down, I get an uncertainty for my input, I get an uncertainty value for my output, and then an expanded uncertainty of the two together. So with this, let's take it to the next one. I'm going to stop sharing, Mike. So, annual calibration exchange. This is what we call ACE. The annual calibration exchange is happening this year in New Orleans. Everyone will get a link to this after the webinar, and this year it's September 18th and 19th. And I believe this is our 6th annual. The first one was in Chicago. The second one was in the corporate headquarters of ISA. Then we went to NASA, we went to Harvard, and last year was near LA at Cal Polytech University. Polytechnic University. Cal Poly. Okay. So that's where we had it. You're all welcome to attend, and this is not an advertisement event. This is a calibration exchange where we all come together and learn from each other and take it from there. At this point, Mike, let's take our next step.
Ned, why do we have to take uncertainty into account with calibration?
Well, that's a good question. You know, uncertainty is a metrology term, which is the science of measurement, and it really is comprised of several different components. You need to consider repeatability, linearity, hysteresis, long-term drift, and other components.
Okay, so with that, then where does confidence level come into play?
Good question. So, we're using statistical averaging to pull these numbers together. And a common method is to use a confidence level of 1 sigma, 2 sigma, 3 sigma. So 1 sigma is not so good, it's 67%. 2 sigma is 95%, and 3 sigma would be 99%. So in our world, the process measurement world, 2 sigma is good enough for the kind of work we do.
Oh, thank you, Ned.
You're welcome.
For more information, check out our description below.
That video makes me laugh. So we're going to move forward, guys. We've seen our little video, and so now we've talked about uncertainty and all these different factors that come into play. So let's take a little deeper dive into the math, and I want to show you how for those third of the audience that maybe doesn't do uncertainty, how can you figure this stuff out? So here's typical calibration data. So over on the left, there's a column for input. Then in the middle, there's the output reading. And then over on the far right, it's got the error as a percent of span. So those are typical things. It's also showing what was used for the input standard and what was the reference standard for the output. But there also are these other columns, uncertainty, and Roy's already kind of pointed those out. So we have the input uncertainty, the output uncertainty, and then we have this expanded uncertainty. So if you look at the input uncertainty column, we're actually calculating how accurate the calibration standard is in making the measurement at that particular test point. So at 400 inches of water, we're saying that the calibrator is roughly plus or minus 2 inches of water, taking in all the different components that Rich talked about, exclusive of maybe human problems. Then at 20 milliamps or 19.92 milliamps, the measurement uncertainty error is 0.003 milliamps or so. So this is instead of talking percent of span or percent of reading, all these other, you can calculate the exact error in the engineering units. But then over on the far right, where it says expanded uncertainty, how do you combine the input and the output? Well, you want to convert everything to a percent of span. So how do we do that? Let's show you the math a little bit. So since we're talking about type B errors, a good statistical method is a way to average things. It's called, a lot of people call it RSS. It's the square root of the sum of the squares. And here's a crazy formula, and actually Rich is going to use this as well. But let's look at that same data, and I'm going to focus on the full scale line, the 400 inches of water data. And here's how it's calculated. If you take the 0.18, divide that by the span of 400, and turn it into a percent, and you square that number, you get this crazy number, 0.00299. 0.0020%. Then if you take the 0.00299 million and of 16 and turn it into a percent and square that, then you get this really crazy number, 0.003492% squared. So if you add those two together, you still got a crazy number, but when you take the square root of that number, you end up with a number that's close to 0.05% of span. So as a mathematical average, we're saying that the combined input and output error is somewhere around 0.05% of span. And if we go back to the data, and we've picked up these three columns, and it's maybe a little hard to see, but Roy showed it in his. He had a huge uncertainty for the 300 PSI module he used to make that low inches of water measurement. In this example, the expanded uncertainty is very small. It's 0.5% as compared to the 1% tolerance. So, in fact, and remember, we have or window of what the true measurement is just a numerical estimate with a 95% confidence level. But in this example, it's a 20-to-1 ratio. The standards are 20 times more accurate than what you're trying to achieve in the process. So this is a test uncertainty ratio, or you'll see the term TUR. And you should note that a 4-to-1 is sort of the normal practice. It's kind of an old military practice that you want your standards to be 4 times more accurate than the process instrument that you're trying to test. So with 21, you've got really good coverage, and this should do you well to accommodate for inconsistencies in temperature in the field and other factors that Rich is touching on. So I'm going to turn this over to Rich and let him get into some more details, but maybe you can take this information and apply it to your world.
Okay. So contributing factors. Can you hear me now?
Yes, sir.
So temp code. All your measurement and test equipment have operating temperature ranges. So let's say it's 18 degrees C to 28 degrees C. So how do you know that you are within that range when you're actually making your measurement? Well, what you have to do is you have to actually whip out your thermometer and take a measurement of the ambient temperature. Now, you saw in Roy's demo, one of the things he had to do in his automated calibration was he had to enter temperature and relative humidity. So that's what that was for, was this whole temperature coefficient thing. If it's within the operating range, you don't have any adders. If you, outside of your operating range, for example, I mentioned the top end was 28 degrees C for an operating range. You might be at 29. So how much does that affect your calibration? So a typical TempCo that I used to work with was 0.05 degrees C per degree C outside of the operating range. And that was good all the way up to, like, say, 50 degrees C ambient temperature. Above that, you shouldn't use it at all. So that just gives you an idea. You can see where this TempCos can add up pretty fast, where you're going to be at a couple of tenths of a degree just when you're like a few degrees out of range. So when's this going to apply? Could be cold outside, like it is where Roy is right now, or it could be hot up on the roof in the summer where you might be having to take measurements, or up in the ceiling of some factories. It also could be hot near some of the equipment. Maybe you're in a heat treat factory and you're working near furnaces, checking the temperature sensors on that furnace. They generate a lot of heat, and so you have to take measurements of your ambient conditions to make sure you're within the operating range of the test equipment. Otherwise, you'll have additional adders that have to be put into your calculation. So then the next item really here is resolution. There are two to consider: the resolution of the test equipment and the resolution of the unit under test. And we combine that at a rate of 1/2 the resolution of the display. So with resolution, you consider this at a rate of 1/2 the resolution of the display. So in the case of Roy's demo, his pressure module had a display reading of 0.0 or 0.1 for the display. So that would be added in as a contributing factor at a rate of 1/2 of that lowest resolution, or 0.05 of whatever the engineering scale is that he's using. I think he was using inches of water. So I guess the other thing here is you only consider the resolution of the measuring device. This could be the unit under test, or it could be your test equipment, or it could be both. And I think in Roy's case, it might have been both. No, he was using the transmitter, so it was just the measurement device under, or the test equipment display resolution that we're considering there. If he was measuring or calibrating something like a digital display or a analog display or an analog pressure meter, you'd have to consider the resolution of both devices because they're both measuring. So, okay, let's move on to the next items here. And so now the temperature gradients along the extension wire for a K-type extension wire, the error for a 30-degree temperature gradient across the length of that whole extension wire that you're using is 0.165 degrees C if there is a 30-degree gradient. So we used to do a lot of calibrations in heat treat shops where we're working around furnaces, and a lot of times the hookup for the temperature sensor was in the back of the furnace where it was very hot, but our calibrator had to stay out in front where we could see it and manipulate it and stuff like that. So we had to use extension wire. We used that 30-degree gradient across that entire length of wire as a worst-case scenario. There are ASTM standards that will give you the exact amount of error per degrees C of gradient across your extension wire. So this is just an interesting contributing factor. It's an example of the effect of a factor that is specific to a function and the setup of your M&T of your test equipment. So another one would be the temperature or the pressure gradient across tubing, which is generally negligible for under 10 feet of hosing. But if you get a real long distance, a whole lot of tubing in your setup, you can actually have a difference in pressures from the source end to the other end. So the bottom line here is you have to really know the function that you're testing. You have to know all the things that go into making that a good measurement, and take that into consideration in your calculations. So then the last thing on this slide is the calibration of your test equipment. Your calibration certificate should list the uncertainty of the calibration either by stating it for each individual test point, or more than likely by making a more general statement like TUR is 4 to 1 or better for all measurements unless otherwise noted. Either way, that's a contributing factor that you need to take into consideration and combine with other contributing factors when you're trying to calculate total uncertainty. See here. So, lastly, I want to talk about the procedure you're using. These are your methods. Has a lot to do with how your people have been trained to do the particular calibration, and just knowing what they're doing, knowing their test equipment. So an example of this would be a specification that assumes the calibrator has been stabled at environmental conditions by being switched on for 90 minutes. That's a long time, but for the purpose of discussion, 90 minutes for measurements done before that thermal equilibrium has been reached. You have an uncertainty adder of 0.15 degrees C. So if your M&T, your test equipment manual, makes a statement like this, You can't just go from the trunk of a cold or hot car, say, walk into the factory floor and take your measurements right away. You need to wait for the test equipment to come to thermal equilibrium with the environment it's being used in. This is actually a thing that we got burned on early in our attempts to get 17025 accredited for field calibrations, because we had guys doing exactly that. They weren't waiting for it, and so it was a write-up, and we had to change our processes and procedures to make up for that. Other functions have their own potential procedural issues, and an example of that would be pressure measurements, where if you're not properly zeroing your equipment, checking for leaks in your hose setup and stuff like that, you could invalidate your measurement. So the takeaway here is read your manuals carefully, know your test equipment, and follow good operating procedures at all time. It's very critical to whether your measurements are going to be correct or not. All right. So we combine contributing factors using the RSS method. So this is exactly what Ned was talking about. The RSS method is the root sum of squares. As you can see in the lower right-hand corner, it's kind of an intimidating equation if you write it out mathematically. But really all it is you take all the contributing factors and you square them. Then you add them together. Then you take a square root of that result. So now going down, we're going to show you a couple of examples of what the RSS method does for you. And it actually helps you a lot because it makes your largest factor the dominant factor, and it kind of weights smaller factors less. So if we combine two contributing factors that are equal, that's our first example there, 0.5 combined using RSS with 0.5 equals 0.7. So it's almost 1.5 times the larger number, or the original number that you come up with. And then in the second example, that should be 0.5, not 0.5. But we're combining that with 0.125. This is an example of a 4-to-1 TUR. And you can see your larger number was 0.5, and a 4-to-1 ratio just gives you that 0.01 additional amount of error. On the bottom, we're showing you what a 10-to-1 combination would be. So you have a 0.5, you're combining it with 0.05, which would be, divide by 10 from the original number. And now you're getting into an insignificant amount because it's way up there at 0.5025. Depending on how much resolution you're showing when you report this data, that might not even show up. You'd probably round it down to just 0.5. So let's see what else. One note is what can you RSS together and what can you not? In the world of calibration uncertainty, there are two kinds of contributing factors. They're called non-correlated and correlated. So the first one, non-correlated, is where the contributing factors are independent of each other and you can RSS them together. How you recognize this on a spec sheet is it'll always be a plus or minus kind of spec, plus or minus 0.05% scale, for example, right? And then you have correlated, which means that the factors are not independent. In this case, you'll always see the word add, and this is true of the internal temperature compensation, our reference junction compensation that we used in one of our earlier examples. When you see that on a spec sheet, it will say add 0.2 degrees C. It won't say plus or minus, right? So what this means is it has to be added to something, typically the accuracy spec. So what you do is you add that to the accuracy spec before you go through the RSS combining process. And I think that's it for me. I believe we're moving on to another live demo where Roy's going to show us another calibration, this time with an correct size module.
Are you sure that's a good idea to bring me back on? You might want to rethink.
I think so. Because I was running out of breath. I didn't pause too much there.
So what I have here is another test. Let me go to Documenting Calibrator. And we already did PT207 with the wrong standard. And let me go to the correct one. So this one is using a 30 PSI module. Again, I'm calibrating 207 inches. And my first one was using a 300 PSI, which is just monstrous for this little test. Let me start up here, and let me vent out my pressure module. I always want to zero out my pressure module before I start the test. So this changes with barometric pressure every single day. Let me hit 0. I'm not zeroing the transmitter, I'm zeroing the transducer of my calibration standard. Okay, again, I don't want to measure 0 on a differential pressure, so I'm closing my vent, and now I'm increasing to about 1%. And I overshot it a little bit. And as Rich mentioned earlier, my first test, I only had 1 digit of resolution on that 300 PSI. On this 30 PSI, I have an additional digit, so now I have 2 decimals of resolution. And here's 2.25. Okay, let me hit start. And I have this automatically, once it stabilizes, I've got it set to automatically grab the next test point. And that's what you're seeing here. So I have this gray bar, which I've designated as within 4% of my target. And that gives me a target to aim at, so I don't have to get it exactly at, let's see, 103.5, which is what my next one is. I just get it into the gray bar, and it calculates the input against the output, and my error is at the top of the graph. My error now is negative 0.0. 20 down to negative 0.016. It's changing. So let me grab my next test point. And again, I'm just squeezing gently on this pressure pump. I could be using the fine-tune knob, but if I can do it through the normal method, I'll do that. Okay, so I overshot it a little bit, but that's okay. Okay. My maximum error was 0.019% of span. Let me arrow down. You know, this one wasn't actually calibrated by Clark Kent. This was, you know what? I'm going to do I Am Batman. There we go. So this is calibrated by I Am Batman. Here's our graph. This looks really good. Here's the numbers that we didn't have to write down because they're recorded automatically. Now, there are temperature values that are recorded by the calibrator automatically, and that's the input calibrator. That's the pressure, the temperature of that pressure module specifically, because this is temperature compensated within the calibrator itself. And the output calibrator is where we're measuring current. I'll put in the same values. 72 is my ambient temp, and I'll put in 15% humidity. And the actual temperature of the device, I'm leaving that blank. I'll save this as both as found and as left. So I'm actually done here. Let me disconnect from here, and I'll fire up my calibration software. And there was a question on what software I'm using, and it's called CMX is the software that I'm using. I need to unload these test results. So I'll connect to find out what I've got, select everything, receive, and they've both come over. So I can look at my individual test results, which is here, but let me do this. These are the graphs. The bottom one is the first one that I did with those uncertainty guard bands that are just monstrous. They're huge, and that's using the 300 PSI module to calibrate something that's 207 inches. So the top one is using a 30 PSI module, and we can see that with the expanded or with the uncertainty, that every single one of those we can be confident to a 95% confidence level that everything is passing. And visually, this is what uncertainty looks like. Again, visually, this is a representation of uncertainty. One other thing let me show you is inside the software, again, your software should be able to perform and calculate uncertainty. Uncertainty process. So if you want to, you can not use software that does this, and you can grab this formula and you can add it all up, do the math. But for me, I'd rather have the software do it for me. So this is the expanded uncertainty of a reading. One last thing. This is the last one that I did, and you can see the uncertainty bars, but we can also see that the input uncertainty, you know what, let me bring up the other one as well. The input uncertainty on the very first one, on the bad one down here, 0.8 inches of water is our uncertainty on the input. The input on the better test, the better uncertainty, is 0.08. That's a factor of 10. So we're 10 times better on the uncertainty on our 30 PSI module. And with that, I'm done with the second live demo. Now, there is a Beamex blog. We do have a blog, and we have 3 individual calibration uncertainty white papers that have been written on this, and there will be a link to all 3 of those on the email that we send you after the fact. So again, there are 3 uncertainty white papers published by Beamex on that. And with that, I think we're ready for the Q&A session.
All right. Thank you, Roy. Hi, everyone. This is Katie Turner with Beamex. I'm going to be moderating the question and answer session today. We did have quite a few requests for a copy of the PowerPoint slides, so I will send that to everyone following the webinar, along with a copy of the recording and those additional resources that Roy was mentioning. So let's begin. I have Rich, Roy, and Ned all on the line. I think you can see their handsome faces. So let's go ahead from Octavio. Ned, would you consider the accuracy as percent of full scale as turn down?
Oh, this is a great one. It depends. Maybe Rich can chime in as well, but I believe if you read any vendor's specifications about turn down, they all talk about that there's a wall at the low end, however they want to say it. So you can only turn it down so far. So used to, it was like 10 to 1 turn down. I believe now most 100 to 1 turn down. So I think you can apply the percent of span to the turn down value as long as it's reasonable. But just know that if you're doing an extreme turn down, like 100 to 1, you need to really read the fine print to figure out what you're doing.
Yeah, I agree, Ned. It's a fine print issue. I think that's why a lot of times you'll have a percent of full scale plus 0.2 or something like that. They put that floor spec on there, so you don't really run into that bottom end because the spec's always greater than the turn down.
Yeah, I mean, in practice, 101 turn down, you might need to spend the money and get a transmitter with a lower range that is going to give you a better.
Mm-hmm. Makes sense.
All right, thanks, guys. Let's move on to the next question. In a calibration certificate, must each measured parameter be traceable?
I'll take a shot at it. If you're using something as a reference standard to make the measurement, you should have if you're trying to demonstrate traceability, then you should have a certificate on that reference standard. Some things that maybe you don't have a reference standard for would be a readout. So if you're doing a loop check, pressure out in the field versus the DCS reading, that indication doesn't have, since you're using your eyeball, it doesn't have a certificate. But you should include, as Rich pointed out, that half-digit resolution should, be counted in an uncertainty calculation, even for a reading. But there is no trace, not certified. Someday maybe we'll figure that out. Another example might be a communicator. If you're calibrating a digital variable, you maybe need to validate that what you see in the field on a communicator matches what's in the control room, but there's no traceability. I mean, the number is, so there's no traceability typically on that. When you get a communicator, it doesn't have a a certificate on it. I don't know, Rich, in the lab, do you have some other examples?
Yeah, I mean, most things are either traceable to a national standard laboratory standard or to a physical standard of some kind, or something like a Josephson junction or a physical chunk of metal that represents a kilogram or something like that. But if you're talking about contributing factors to uncertainty, if you don't know, if it's not listed as, like, say, k equals 2 or k equals 3, you can assume a rectangular distribution as opposed to the normal distribution, which is what you showed when you were doing showing expanded uncertainties. And so what you do in that case is you consider that to basically be square root of 3. So instead of, if you're going to normalize that to k equals 2, you would divide it by the square root of 3, 1.732, I think that is, right? And then you would multiply it by 2 to get it re-expanded. And that would be how you would handle something like, often digital displays fall into this, resolution of a display falls into this category, where it's not stated what it is, so you have to assume the worst case, which would be the square root of 3, which represents rectangular distribution as opposed to a normal bell curve. And so to get it to that place where you combine it with the other ones, you divide by 1.732 and then multiply by 2. So I think that might answer his question of how to handle things that aren't really a traceable measurement per se.
All right, perfect. Okay, we have a question from Thomas. Is there an industry standard for using a TC reading in degrees Celsius?
Well, thermocouples by nature are not as, they're not as accurate as an RTD, and then also the quality of the thermocouple, and also the temperature, the service that you're trying to measure, it greatly increases at the full scale. So when you're trying to measure 2,000 degrees Fahrenheit, or whatever, they can be off by quite a bit. I would think the manufacturer would have an accuracy spec that they would state, but I don't know a common one. Maybe with Honeywell, do they have a standard number they throw out?
There are ATSM standards, right, which describe a particular quality of thermocouple by type and give a specific range of how accurate they have to be for a thermocouple manufacturer to sell it. So most of the thermocouple manufacturers adhere to ATSM standards on that. Can't remember the number exactly. It's listed in 2750, but it's not from that standard specifically. And as in any test equipment, any reference standard, generally the more you pay, the more accurate it is. So if you're buying a really cheap thermocouple, don't expect it to be much better than maybe 10 degrees, but you certainly that can give you and on those cheaper thermocouples, they won't be claiming to meet any standard.
Yeah.
Buyer beware.
Okay.
All right, thanks, guys. We have an LOL from Brandon out there, so you guys made somebody smile today. The next question is from Jim. He says, what software does Beamex use with the MC6 for the calibration certificate, and is it compatible with AMS? And I think Roy answered that earlier, that it is Beamex CMX calibration management software, and yes, it is compatible with AMS. So we'll move along to the more technical questions now. We have another one from Terry. He says, where is entering resolution as half of the resolution indicated, either on the unit under test or the test equipment cited at?
I'm not sure what exactly you mean. For me, it's the GUM, the Guide to Uncertainty and Measurement, which is an international standard full of all kinds of mathematics that tells you how to handle these things.
Yeah, and we're being very specific about half of the resolution. Remember, uncertainty is just an estimate, and you're just trying to get, an idea of where you are. And as Rich pointed out on his slides, you can come up with a number, but you probably ought to have a little extra room, or give yourself a little extra room other than what you just calculate. And like the 4-to-1 ratio, that's giving you that coverage, because there are extra things that you just can't account for every little thing.
Yeah, it's true. And let me just add to, I've had a little bit more time to digest the question. If you think about this logically, internally to the internal display, there's an A to D converter, which might have 9 digits or something, 8 digits, right? The display only has 1 or 2. At some point, there's rounding going on. So if you look at rounding, you're really only going to be half of that 0.5 or whatever that last digit of resolution is off, because it's either going to round down or round up, depending on whether it's 0.5 or 0.4, right? In the case of rounding down at 0.4, it's a little bit less. So 1/2 of the resolution it's kind of a physical property of digital displays.
Yeah, and there's also if you really want to study it, there's an international standard on rounding. It's crazy.
Oh yeah,
it is.
You need to include that.
Rounding.
Yeah.
Yeah, there are definitely arguments about which way to go, but 0.5 will cover you either way, I think.
All right, great. The next question is, can you expand on the difference between test uncertainty ratios and test accuracy ratios?
So TAR and TER. Rich, you're the lab guy. I'm going to let you answer it.
Yeah.
Oh. That's a hard one. They're very similar.
Yeah, I guess we could have another webinar on TAR and TER.
Yeah, exactly. I think the test uncertainty ratio, which I believe is the standard for 17025, includes more different kinds of factors, where accuracy includes less contributing factors to your thing. It leaves out things like like resolution, like factors that are about your procedural way of doing the measurement.
I guess whoever asked the question, they need to Google it.
All right,
so
thanks, guys.
I think that's a good answer, that accuracy is less components. That's going to be the basic difference.
Yeah.
All right. We have a question from Daniel. What if a 4-to-1 ratio cannot be achieved by available standards in the market? For example, in temperature and humidity measurements, what is the recommended strategy?
Okay. Well, you usually have a statement that says something like, 4-to-1 test ratio unless otherwise stated. So the first thing is you're going to have to state what it actually is, even if that's 1-to-1, right? And then if you look at the new 2017 version of the 17025 standard, they address this issue. You can tell it's fairly new because it's a new standard that they're addressing this issue with. And that is you need to come to agreement with your customer. If you can't meet the expected TUR 4-to-1 ratio, you shouldn't just hide that fact from your whoever you're reporting the number to. You need to come to agreement. You say, look, we can't do this. And it does happen. You might be at the very end of what's possible with physics today, right? There's just no way to measure any better. Or you might say, look, at my lab, I can do it only 1-to-1. If you want something better, you got to go to NIST maybe, or something else. They'll usually come to agreement with you and say, go ahead and do it. Just report it the way it is, rather than spending the additional dollars to go to a higher level lab. So with things like that, the bottom line is report it correctly. If you report it correctly, you'll stay out of trouble.
So in Roy's demo today, his first test, it basically was 1-to-1. And so the 300 PSI module is just as accurate as that transmitter at those inches of water. So all you can really do is, if you're 1-to-1, is you can say, well, I checked it, and the point was in the middle, so I feel okay about it, but I sure wouldn't adjust that transmitter. If it was off, you can't say if the transmitter is better than the calibrator. So you can check and maybe say you validated it, you didn't really calibrate it. But there, and as Rich kind of alluded to, you're accurate to get a 4-to-1, it could cost you money. Like instead of buying a plain calibrator, you might have to buy a deadweight tester to make a good pressure measurement, and that can cost you, $25,000. Is it worth making that measurement? One other suggestion would be is to test more often. Instead of, you can't let it go for 6 months. Maybe you need to check it once a month, or even perform 2 tests while you're in the field and just validate your data. So there's things you can do to feel better about it. And it's, as Rich said, it's just good to know that you're kind of dicey in what you're doing. It's at least you know it.
Ned just reminded me of another possibility, which is to use the standard that would normally be 1-to-1 as a transfer standard. And in that case, instead of using like the 1-year accuracy, you'd be able to use the short-term accuracy and repeatability. Really only the repeatability factors in here, where you would transfer the accuracy of another known standard to whatever that is that you're testing out in the field.
Yeah, we have a customer that is checking flow measurements. They use a clamp-on ultrasonic compared to whatever flow meters in series, and they just want to see that it's in the ballpark, that, it's not really a calibration. They're not going to adjust. But if they see the numbers moving apart or it's not where they want it to be, then they know they need to maybe pull that flow meter out and put a new one in, or do something to address the issue.
That makes sense. So if all of a sudden you're getting different readings than you got for the last 3 weeks, something went awry.
Right.
You won't know whether it's your test equipment or your unit under test, but you'll know something went awry.
But those are real-world problems that you have to try to come up with something that elevates your confidence.
Yes.
All right. This one is for Rich and Ned. Can you expand on the type A and B in the RSS method? Well,
I alluded to it. is sort of random type components that you just don't have control over, and systematic, like drift is a systematic problem. You can adjust something and bring it back to true. So I don't know. That's a whole. Rich and I talked about this, and we left it out of the webinar because we could spend a whole hour talking about it. Go ahead.
Yeah, just real quick though. For type A uncertainty analysis, what you do is you take a whole bunch of measurements. You say I say a whole bunch, but like 10 of them, right? Then you have to take the mean of those 10 measurements. You also have to take the standard deviation of those 10 measurements. Then you have to multiply the standard deviation by not only the K factor, but the K factor which includes a student's P factor. So for 10 measurements, you have to multiply that by 2.6, and you have to look up student T tables in a statistical analysis handbook to find out what it is for a given set of measurements, right? And then that result of that computation will be your plus and minus spec around the mean which you originally calibrated. This is generally not done outside of a lab environment. We did it with resistors at my lab, places like, and we had maybe 10 years of data on these resistors. Places like the HP Standards Lab had banks of 10-volt standards, which they had taken many decades of data on. They also had which was really cool, some resistors in a liquid bath, an oil bath, which had been in that same oil bath for 25 years and had never moved and had never changed temperature once in all that time. But for you guys, we say use type B, because the type B components are like the ones we talked about. They're handed down either from the equipment manufacturer or from the other calibration labs that you're using, and they're handed down in an already expanded form. You know, you already have that plus or minus specification that you could develop by taking measurements and putting them through this analysis. So that's why we say you're fortunate that you only have to consider B-type contributing factors, because they can be normalized and combined through the RSS method relatively easily, without having to worry about the quality of all your measurements that you've been taking. And that's the short story.
Yeah.
Okay, next question is from Perry. He asked, can you guys explain the reason for not starting a differential calibration at a 0 value?
Because the curve on a differential pressure goes straight up and down, and then it flattens out. And if you do it at 0, you're on pretty much a straight up and down. Even if you change it a little bit, you're jumping all over the place. If we get in at 1% input, then we're 10% output, and you're starting to at least come across to the curve instead of it being a straight up and down line. Did you guys add anything to that?
Well, you demonstrated a square root transmitter, not a linear transmitter. If it was a linear transmitter, I would test it at 0.
Yes. Sorry, was that the question?
What was the full scale of that? It was 207 inches, right?
Yep.
So at 2 inches, you went from 0 to 2 inches. The milliamps jumps from 4 to 5.6 milliamps. It's this factor of 10.
Yep.
So it's just so noisy. If you just wave your hand by the pressure port, it's trying to sit there at 4 milliamps, but you're going to see it flutter, up to 4.5 milliamps or something. It's just the nature of the signal, as you said, is vertical, and then it starts to. Well, I did it the wrong way, but then it starts to taper off and gets more normal. So for DP sensors on an orifice plate, the flow measurement below the 10% of the output is worthless. It's just not good technology. If you have to measure low flow, you need to get a smaller orifice plate or get a different technology to measure the flow accurately. So it's just a phenomenon of what you demonstrated.
All right, very good. Next question is from Tommy. He says, thermocouple wire temperature gradient is mentioned as a factor that should be considered. But what about bending and kinking of the wire?
Well, thermocouples are a physical device, and if you bend them or kink them, you're changing some physical characteristics of it. It's just not, you want to treat them as nice as you can.
Yeah.
Rich, did that come into play in your lab at all?
No, but we were pretty gentle with how we stored and used those wires. We kept them hanging up on a hook, so they were extended, their full length of 3 feet or something like that. If something got kinked or like that, we would go through a verification process, make sure that it's measuring correctly, and if it wasn't, we'd get rid of it and replace it.
Yeah, in our lab, we use we get a set to do our reference junction, and if we ever have a question about the one we're using, we have a lot of that came out of the same manufacturing lot. They're all certified. We can check it, like you said, do a verification. And then every 2 years, we throw those thermocouples away and get a new set. So we're constantly...
That's good practice. In my lab, we were using external reference junction compensation, which means we were tying thermocouple wire to copper wire. And we kind of had to manufacture that ourselves and test it ourselves. And then using a bath for maintaining that junction at zero, so there would be no voltage generated because of the dissimilar metals. But
yeah, so if you're kinking, if you're kinking your thermocouple wire, just know that if you're within 20 degrees, you're okay.
Yeah, you want to treat them gently as possible. That's even more true with an RTD, which can break just because you tap it.
Yeah, somebody taught me, Rich, if you drop a reference probe, an RPRT or SPRT on, that you're going to cause a zero shift, like just dropping it on the ground. That physical shock, might be small.
Yeah, at the very least
significant.
And then you'd have to send that into a lab where they can determine whether that shift is repeatable. If it's stable, they'll send it back to you with a new zero correction factor, which then goes into your Van Dusen equation to produce the temperature. Yeah?
Right.
I think I said that right, Van Dusen.
Calendar Van Dusen.
Yes, that sounds right.
All right. We have many, many more questions, so we'll get through as much as we can. We can go for about 5 or 10 more minutes here today. The next question is from Philip. He says, hey guys, thanks for today. Let's say we have a 3051S for flow, and it is the Ultra for flow model. The spec sheet says it can be performed at plus or minus 15%, 0.15% of the reading, 0.15% of the reading. All of the fine print criteria is met: temperature, relative humidity, within spec turn down ratio for URL. The CMX calibration records indicate that it is one data point, let's say the lower flow range, that is not meeting our plus or minus 0.25% cutoff. How can we use uncertainty here? Today's example showed percent of span criteria. Shouldn't we use percent of reading for flow?
Yeah,
you could.
You know, if you noticed, I divided the uncertainty by the span to get the to convert from engineering units to a percent of span value that we could then square and square root to get a final. So on a percent of reading, there's still an uncertainty at that point. I don't know, Rich, I guess I've never done a percent of reading. It works the same way, doesn't it?
Yeah, it works essentially the same way, but the reason we usually do for percent of full range or percent of span is it gives you a worst case measurement that you can use for any test point in that group, you know, within that range. If you use a percent of reading type of thing, assuming that the device is spec'd that way, you're going to have to recalculate for every test point because every test point is going to be a different reading, so a different number will result.
One thing
I'm not sure
with that is if your first, yeah, I'd like to add one thing is if that 1% is still too far out as far as the uncertainty, then increase it to 2 or 3%. Increase the input, and you'll flatten out more, and your uncertainty will actually be less. And that's as long as your process isn't designed to be measured around 1, 2, or 3% of span. There's one way to get around it.
Yeah, I might have to. We're going to get these questions. You know, after the presentation, I'm going to have to get my calculator out and take a look at that one. That's a good question.
Agreed.
All right, excellent. All right, next question is from Julio. Hi, Roy. On the CalGraphs, can you explain the difference between the two uncertainty indicators, the good and the bad?
The difference between the two uncertainty indicators. Julio, good to hear from you.
One was big and one was really small.
Yeah, I was just bringing them up on my screen. I realized I'm not sharing. But, yeah, the guard bands on the bad one were actually exceeding or at the tolerance level that we were at. And the good guard bands were a lot smaller and less than, they're about a 1-to-4 ratio, maybe 1-to-5 overall. Mm-hmm. And I took these measurements at a 0.25% of span. I put it tight on purpose. And for this transmitter, I probably would have had it at about a 0.4% or maybe even 0.5.
All right, great. Thank you. Okay, Philip asks, what variables do I need to enter into CMX for the uncertainty bars to be accurate? Today's example showed temp, relative humidity, etc. being entered by Roy.
So with this example, that actually comes over automatically from the calibrator. There's a standard temperature deviation, that's not the word I'm wanting, but actual temperature error that can be calculated. And then there's a difference in temperature reading. So per degree C, there's so much of a change. And that gets reported automatically back to the software from the calibrator.
Yeah, if you had entered the ambient temperature was 95 degrees Fahrenheit or something high like that, like it might be on a hot day in Louisiana, there's the formula behind the Beamex system would add the additional error. So it would make the uncertainty bar, you know, if it was 72 degrees and it was this far, if it was 95 degrees, it'll add that additional error due to the high temperature. We have a nuclear power plant customer. They're calculating error with an ambient temperature of 120 degrees. So when they're down in the very depths of the reactor, they have these extreme temperatures that they have to deal with, and they analyze, well, how good is the test equipment under those conditions? And it's definitely can be significant depending on the equipment. I guess the answer to the question is with CMX, it's built in. But if you're a lab like Rich, you have to account for these things in your uncertainty budget, calculating up all the different parts that give you total uncertainty.
Okay, great. This one is somewhat related, this next question. So it says, in regards to the calibration software, how much for calibrations is preset and how much is manually entered?
Say that again, Katie.
In regards to the calibration software, how much is preset and how much is manually entered?
The uncertainty info or the actual test data?
Yes, in the Beamex software, if you want to enter in a gas sample bottle or a pH buffer solution, you have to manually enter in the uncertainty data. That's there's not a standard one to pick from or something like that. So really, what Roy demonstrated, we have all the information for our calibrators built into the software, so you don't have to enter in anything for a calibrator or for a keyed entry number. Those numbers are all accounted for. But if you want to have the software calculate uncertainty, then you do have to enter in the components for the given reference standard.
So the software is capable of doing a custom setup by the user, basically.
Right.
Yes.
And you can even pick windows of operation, like if it's like for a thermocouple, it's not as accurate when it's freezing, and then it gets a little better from 0 to a medium level temperature, and then it opens up at a high temperature. So you can put in those different ranges. See, or uncertainty.
All right. We are going over our time here, but I think we can keep going for a few more minutes. So Stephen has a question for Rich, and he says, could Rich provide some more information regarding the additional error introduced when having to use more than 10 feet of tubing or hose from the source pressure to the test instrument?
Okay.
Yeah, Rich.
I don't have that chart in front of me right at the moment, but this is they're known quantities for certain diameter tubings. I'm pretty sure in my archive I have the chart for that, so I can look that up and try and respond to that after the fact. But don't have the numbers right on top of my head.
So if it's like a capillary type tube, does that perform better over 10 feet than a like refrigerator ice maker tubing?
I would think so.
Yeah.
Because it's smaller diameter, less flex in the tube. But it's mostly related to length, I think.
I would be, if I was in a process plant, I'd be most concerned if I was down on the ground and the transmitter was way up high on a catwalk, and you're going to have a pressure differential just from the altitude, if you will.
Right. pressure gradients.
All right.
Wait,
Roy,
I see a question for Roy. How did you get rid of all the smoke?
Rude. Hey, I'm not answering that. It was a motion like this.
Yeah.
Before I turned on my webcam, I was doing this a lot.
That was a good one.
All right. We'll take this one last question, and then the rest of the questions that we were not able to get to today during this session, the presenters will follow up with you on personally via email. Okay, last question. How often should we calibrate calibrators?
The calibrator vendor should specify that for you. They should tell you.
It depends on your risk and your usage. Normally, I think 1 year is correct most of the time. But you can, there are other standards like heat treat standards that demand, 3-month calibrations for certain types of test equipment, or I should say test equipment that's being used for particular kinds of tests. In general, you can increase your calibration interval based on past performance if there's no other standard demanding or requiring you to do otherwise. So that question has to be really specific for us to give you a solid answer on.
Well, one thing I'd like to add to that is if you have a 1-year uncertainty and it's this, if you have a 2-year uncertainty, then it could be double that if you wait 2 years to calibrate that same calibrator. And you need to know, is this number okay with you? If you need this, then it needs to be annually. So we really need more data to answer that.
And an example of high risk, I know that nuclear power plants put calibrators on even though they're annual, they put them on a 6-month window because if a calibrator comes back with a failure, they have to do a mile-high paperwork analysis of what did that calibrator touch, and so they just can't tolerate
affected by it.
So the risk is so high they'll even derate the calibrator spec and put it on a 6-month cycle just to avoid any possibility of that.
Right, makes sense. In our lab, even when we got something in that was supposed to be a year, we would do regular verifications, which were really the equivalent of a full recertification as far as the data we took. And we do that every month until we got 3 months worth of data, and then we'd expand it to 3 months. And so it would take us almost 2 years to get that thing to the point where we were confident enough to let it go a full year without looking at it. And that was just because of the risk of recall. When you're a calibration lab, you don't want to be calling up your customers and saying, "Oh, you got to send your device back in to get recalibrated." They tend to get upset with you.
Yeah.
In particular, those nuclear customers that you're referring to, Ned, we had a couple of those too.
Yeah, they're not happy when that happens.
All right. Well, thank you, everyone, for this very lively discussion and all the questions that came in. And, again, we do have a good bit of questions that we were unable to get to. But rest assured that one of the presenters will be in touch with you personally to follow up. So one last comment is that we got another LOL from Brandon. So Brandon is a happy guy out there. And I'll turn it back over to Mike to conclude the webinar.
All right, very well. Thanks, Katie. On behalf of ISA, we would like to thank you all for your participation in today's event. If you did miss any portion of this webinar or would like to rewatch the recorded version, we will be emailing all registrants a link to the recording along with additional links for supporting information. Post-event survey will appear requesting your feedback. If you would take a moment to complete this survey, as it will help ISA plan future web events. This will conclude our program for today. Thanks, everyone, and have a great rest of your day.